to this last day of the conference. And before we really start, let me do some formal announcements. This is all the talks are recorded and live streamed, and if you are not happy to be recorded or live streamed or whatever, you can turn off your microphone and camera off, and you can ask questions using chat. And okay, the other announcement is that there is very entertaining live transcript at the bottom of the screen. So if you enjoy sort of the fun side of it, you can keep it, but otherwise it's very easy to get rid of it just by pushing some button at the bottom of the screen, and you no longer have this interesting version of talks. Okay, so after these announcements, it's my great pleasure to work on the first speaker today, Lilian Matthiesen, who will talk about contributions of additive combinatorics to the study of rational points. Lilian.
Thank you very much. Thanks for the introduction. Thanks to the organizers for the invitation to speak here. It's quite an honor. I will speak about contributions of additive combinatorics to questions concerning the existence and distribution of rational points and certain families of varieties. This is an area where Swinnerton-Dyer has made early headway, and as has been highlighted in Alexei Skorobogatov's lecture yesterday, has been involved in many of the subsequent developments. I will focus here on results that have been achieved with input from additive combinatorics. And before I will speak about any of the results about rational points, I would like to provide some background on additive combinatorics, and I would like to give an overview of the type of results from additive combinatorics that turned out to be relevant to this area. And I will survey at least some of the developments within additive combinatorics that led to those results. So let's start. What kind of questions are studied within additive combinatorics? A lot of the problems studied here have the flavor of an inverse problem. That means you observe your object through some measure or norm. You are given the information about the size of that measure or norm, and you would like to deduce from this information structural information about the object. Here's a fundamental instance of such a question. We let capital N denote a parameter that runs over the natural numbers. And now let's consider a set that sits inside the first n natural numbers. How large does the set have to be in order to guarantee that it contains a non-trivial arithmetic progression? How large does the set have to be in order to guarantee that it contains a configuration of the shape n plus d, n plus 2d, where we insist that d is a positive integer in order to make this configuration non-trivial? If you choose a to be the full set of integers, there are lots of such configurations. But can we give some non-trivial upper bound on the size of a that still has this property of guaranteeing, lower bound, I mean, of guaranteeing such configurations? The first substantial result on this question is due to Roth, who proved in a highly influential paper from 1952 that any subset of the integers up to n that does not contain a non-trivial three-term arithmetic progression has size at most little o of n. Following Roth's result, there has been a huge amount of effort trying to improve these upper bounds in Roth's theorem. In the course of improvements on Roth's theorem, a lot of new techniques have been developed. One of the aims in improving the bounds has always been to improve the bounds thus far that this result, which is a very general result about subsets of the integers, can be applied in the setting where we are considering the subset of primes that sit inside the first n integers. There are roughly n divided by log n primes in the integers up to n. So in order for this result to apply to the set of primes, we would need a bound instead of this little o of n, a bound of the shape little o of n divided by log n. And building on essentially all of the subsequent development, this has been very recently achieved on the work of Bloom and Sisask, who prove that a set in the integers up to n that does not contain a non-trivial three-term arithmetic progression has size at most n divided by log n to the 1 plus some positive absolute constant c. So this result applies to the set of primes. If you look at the shape of Roth's theorem, there are several ways of generalizing this result. One is to ask for, instead of three-term arithmetic progressions, longer arithmetic progressions. A different way of generalizing would be to exchange this particular configuration by configurations of different shape. And there has been work in both directions. Here's one of the latest results into the latter direction, where Pelouse and Prandtl managed to prove that a subset of the integers up to n that does not contain a configuration of the shape n plus d squared, where d is non-zero, has size at most this quantity. So we also have explicit upper bounds, very good explicit upper bounds in this setting, but in this case, the results are not strong enough in order to apply to the set of primes. Let's take a look at the other direction where you replace three-term arithmetic progressions by longer progressions. In this direction, Semeredi proved in 1975 that the analogous statement to Roth's result holds. So if you take any k larger or equal to 3, then a subset of the integers that has no non-trivial k-term arithmetic progression has size at most little o of n. Following Semeredi's result, which was proved using methods from combinatorics, new proofs have been found. First of all, a proof by Furstenberg from 1977, which proceeded via ergodic theory. And then for the further development of additive combinatorics, extremely important, a proof by Gowers, who was aiming at generalizing the proof strategy from Roth's original proof. So Gowers produced a number theoretic proof that used methods from discrete Fourier analysis and combinatorial ideas. The reason for which this proof is so important is that it constitutes the start of what is now called higher order Fourier analysis, and it introduces what are now called Gowers uniformity norms. And I would like to say a little bit more about what these Gowers uniformities are and what they do. So let's take a look at the subset A of the integers 1 up to n. And let's denote by 1 sub a the indicator function of the set. So 1 sub a is a function defined on the first n integers and is a 0, 1 valued function. Let delta a denote the density of the set A within the integers up to n. And then consider the function h sub a, which is the difference of the indicator function and its density. H sub a has mean value 0. And now Gowers uniformity norms are constructed in such a way that the following holds. If this balanced function h sub a has a small uniformity norm of order k minus 1, then A contains the expected number of k-term arithmetic progressions. I will say in a moment what expected is. So if the uniformity norm of this centralized version of the indicator function is small, we will find arithmetic progression, and we will not only find one, but the expected number of them. This is not so difficult to establish. What is extremely difficult is to say something into the other direction, to analyze the situation where the uniformity norm fails to be small and deduce structural information about the set A. So this problem is what is the difficult part of Gauss's work. This problem is not completely solved within the work, but the work lays the foundation, together with some developments within ergodic theory, for all of the later work on this inverse problem. I promised to say something about the expected number of k-term arithmetic progressions inside the set A. So here is a reminder of the notation. And with this notation, we can now express the number of k-term arithmetic progressions within the set A by this first sum here. We parameterize the set of all arithmetic progressions within the set of integers up to n using integers n and d. And then we test for each element of this progression whether or not the element lies inside A. So this first sum just counts the number of k-term progressions inside A. Now we replace the indicator function by the function HA plus the density and obtain the next expression. And here we may multiply out the product in the sum. If you multiply out, you pick up one contribution that comes from selecting each constant term in each factor. And that contribution gives you the density to the kth power times, when you look at what the sum counts, the number of k-term progressions inside the set of integers up to n. And this first term here is what was meant by the expected number of k-term arithmetic progressions. From the other terms that occur when you multiply out, you pick up 2 to the k minus 1 further sums, and each of them involves some instance of a factor HA. And the claim is then that if the uniformity norm of HA of a suitable order is sufficiently small, then each of these additional sums only contribute an error term to the expansion of our counting problem. If you look at the definition of uniformity norms, you might see that the shape they have is one that interacts extremely well with sequences of applications of the Cauchy-Schwarz inequality. So proving that each of these additional sums are small proceeds via a long sequence of applications of Cauchy-Schwarz intertwined with certain applications of changes of variables, but uniformity norms are constructed in a way to handle such expressions that occur when you apply Cauchy-Schwarz a large number of times. I have written here the expression for the U2 norm. When you go to higher order uniformity norms, the number of factors doubles with each step. The U2 norm is very interesting because it has an alternative expression as a sum over Fourier coefficients of the function that you are looking at. And why is that interesting? It is interesting because it allows us to examine the case where the uniformity norm of such a function HA is large. If the U2 norm is large, then at least one of the terms in this sum must be large. So if HA has a large U2 norm, it must have a large Fourier coefficient. And if HA is a function that has mean value 0, the 0 Fourier coefficient vanishes. So in fact, HA has a non-trivial Fourier coefficient that is large. You can reformulate this latter expression as saying if the uniformity norm, the U2 norm is large, then HA correlates with an exponential that has a linear phase function. Information goes into the other direction as well, and it turns out that Fourier analysis is enough in order to completely solve the inverse problem for the U2 norm. Fourier analysis is also enough in order to understand the counts of three-term progressions and dense subsets of the integers. When you would like to understand how k-term progressions for k larger than 3 behave in subsets of the integers, you will have to understand higher order uniformity norms and solve the inverse problem for those, or at least deduce quite a lot of information about this inverse problem. In this regard, it is important to note, and this is one of the things that is contained in Grau's paper, is that an equivalent statement to the one about the U2 norm is no longer true for higher order uniformity norms. So the implication that the UK norm of HA is large implies that HA correlates with an exponential with a linear polynomial phase function. This is false. Fourier analysis turns out to be insufficient to describe these higher order uniformity norms, and you can construct examples of subsets of the integers up to n that show that Fourier analysis is insufficient in order to understand the number of k-term arithmetic progressions in such sets for k larger or equal to 4. So more work is needed here. Let's move on. So far, the results that I mentioned all have the shape. We make some assumption on the size of A, and if this size is sufficiently large, we can deduce that a certain structure can be found within A. The bounds in Semerides' result, definitely if K is larger than 4, are not strong enough to apply to study the set of primes within the first n integers. So if you nonetheless would like to prove a result, a Semeridi type result, inside the set of primes, you will have to make use of additional information about the set of primes. So the results stated before were completely general. They made no assumptions about the sets A. Now, if we want a Semeridi type result in the sparse setting of the primes, we need to work with information about the primes. And the type of information that Green and Tao used in order to succeed with their result was a transference strategy. In a simplified manner, very roughly, what happens is that you replace the characteristic function of the set of primes by a dense version where you weigh logarithmically and replace it by the von Mangold function. So the von Mangold function is such that it has density 1 in the set of integers up to x. And Green and Tao proved that whenever you consider the von Mangold function up to some cutoff parameter x or up to some cutoff parameter n, then you can decompose this function as a sum of a function that is bounded, a function that has small uniformity norm of some chosen order, and an error term. And now, if you would like to study the number of k-term arithmetic progressions in the integers up to n that are weighted by the von Mangold function, you can discard this error term. The term that has small uniformity norm has only an error term contribution to this counting problem, and you are left with the task of analyzing how many progressions there are in the set of integers up to n, weighted by some bounded function. And this is a problem to which the tools developed in the study of Semerides' result in dense subsets of the integers, these tools apply to the problem where you weight with a bounded weight function. So you manage to transfer the result from the dense setting to the sparse setting. Now, I mentioned before that generalizations of Roth's result include looking at different types of configurations. And I would just like to briefly mention that you can study certain types of polynomial configurations within the set of primes. And here you fix polynomials with a couple of conditions. You need to make sure that there is no obvious reason for these shifts of polynomials not to simultaneously represent primes, but you fix certain polynomials and you can show that there is a shifted copy of this configuration within the set of primes. This result is stated out of the historical order, and I would like to return to the situation of finding long arithmetic progressions in the set of primes. Following this result, Green and Tao, in collaboration with Ziegler, continued to study the inverse problem for the uniformity norms. And they eventually managed to prove that a bounded function with large uniformity norm correlates with objects called near sequences. Near sequences are generalizations of the exponentials with linear polynomial phase functions that we met before in the U2 norm case. Why is this result interesting? It is interesting because it gives us an alternative description of functions with large UK norm. And you can use this description in order to prove that a specific function you are looking at has a small UK norm. Here's an example of how this can be done. Green and Tao showed that if you take the von Mangold function and subtract of its mean value, then you obtain a function that is orthogonal to near sequences. At least if you remove the contribution from small primes. This statement, you would like to apply to this statement the inverse result in order to deduce that the von Mangold function is equal to a constant plus a function that has a small UK norm. That can't be directly done because the von Mangold function is not bounded, and this result is a result about bounded functions. So you have to recall that there is a transference principle available for the von Mangold function, which can decompose you the function into a bounded part, one that is of small UK norm and an error term. And if you combine these two statements, then you can apply the inverse result and still deduce that the von Mangold function is equal to a constant plus something that is small and a UK norm. And now, this allows us to prove much more general results than before. Before, there was this unspecified bounded term coming up, and all that was possible was to say there exist progressions within the set of primes of any given length, and arbitrarily many of them. Now it's possible to count asymptotically how many progressions of a given length k there are in the integers up to x. And moreover, instead of just counting progressions, you can count asymptotically how many solutions there are to certain systems of linear equations within the primes. If you look at this last result here, this is not entirely a result about primes. There's only part of the result that is about primes, and this is what is written in the middle of the slide here. We use that von Mangold function -1 is orthogonal to near sequences, and we use that there is some transference principle available. The rest of how this proof goes is something that is about a more general setting, and this opens up the possibility of investigating such expressions for more general arithmetic functions replacing the von Mangold function. And there I want to continue now. So we consider the setup of what was on the left-hand side in Green and Tao's 2008 result. In this setup, we have a collection of linear forms, phi1 up to phi(r). These are forms in S variables. And in order for the proof to go through, they have to satisfy the condition that they are pairwise non-proportional. For each of the forms, we fix an integer shift, and we consider now, instead of the von Mangold function, arbitrary arithmetic functions, h1 up to hr, which are functions defined on the natural numbers. And now we consider what I denote as a linear correlation of these functions h1 up to hr. We consider an expression where we evaluate the jth arithmetic function at the jth form shifted by the jth constant. These products are summed over lattice points that are restricted to some set t times k inside R to the s. K here is a fixed set. It is nice, it is bounded and convex. And t is a scaling parameter, which we will let tend to infinity. Now the question is, can we understand these linear correlations asymptotically as t tends to infinity? And the strategy of the result due to Green and Tao allows one to do this, provided we can prove certain things about the arithmetic functions h1 up to hr that in some way correspond to the information that was previously used about the von Mangold function. So we really have to work with information that comes from these specific arithmetic functions. What kind of information is needed? We need to know that we can use the transference principle. So we need to be able to decompose these functions into a bounded part, a part that is Gauss uniform and some error term. And we need to be able to show that each of these functions, when you subtract of its mean value, is orthogonal to near sequences. These are two substantial tasks that need to be carried out. Potentially, you need to make some modifications to the setup. So there are two tasks that need to be carried out in order to deduce asymptotics for such expressions star. I did this for a few functions quite a long time ago. I considered the divisor function. I considered the function that counts representations of the argument as sums of two squares, and the generalization of the two that counts representations of the argument by binary quadratic forms. If you look at the collection of functions written up here, then all of them are counting functions. All of them count how many representations are there of the argument in a certain way. Representations by certain binary quadratic forms in this case. When you consider expressions of the shape star with arithmetic functions given by counting functions, then you can reinterpret star as a count of integral points on certain varieties. And I would like to show this in the case of the representation function by sums of two squares. So we now consider the case where each function hj is given by the function that counts representations as sums of two squares. In this case, when we look at star, what is happening? For each of the arguments in this product, we count the number of solutions to such an equation. This product counts the number of solutions to the system of equations. And now the x variable here is restricted to lie inside the set t times k. And this means, since k is something fixed, we are essentially counting solutions to the system of equations, which are of height bounded in terms of t. What else can you do with asymptotic evaluations of star? If you can show that star has an asymptotic evaluation, which has a leading constant that can be interpreted as a product of local factors, and has the property that as soon as all of these local factors are positive, the product still converges, then you can prove a Hasse principle for solutions of the system of equations. As soon as there are local solutions at all places, you can choose your parameter t sufficiently large for the main term to dominate, and then you know that you have a positive quantity here. So star has a positive contribution, which means there must be a solution to the system of equations. The shape that star has is sufficiently general to not only study Hasse principle, but it also allows one to study weak approximation. Why? Because there's a lot of flexibility in choosing these linear forms, and you have a lot of flexibility in choosing the shape of this set K. And I would now like to explain how results of this form can be used to study rational points in a somewhat more general setting. And for this, I will start with a quote from a paper of Birch and Swinnerton-Dyer called the Hasse principle, the Hasse problem for rational surfaces. This is a paper that was already mentioned in Tim Browning's talk. And Birch and Swinnerton-Dyer write in the introduction, we define the Hasse problem for a family of varieties to be 1, to determine whether the Hasse principle holds for the family, and 2, if not, to describe the obstruction to the Hasse principle for this family. In this paper, a lot of families are discussed that fail the Hasse principle, and they are discussed in the light of the Brouwer-Manin obstruction, which was fairly new at the time this paper was written. I would now like to continue to discuss this Hasse problem for one specific family of varieties. To motivate this family, let's consider the following setup. We fix a finite extension of the rational numbers of degree n, and we fix a polynomial with rational coefficients. And now it seems to be a quite natural question to ask, what can be said about the set of points at which the polynomial takes values that are representable as the norm of some element of the extension that we fixed. If you choose a basis for k over q, you can reformulate this problem as one concerning the set of rational points on a variety that is described by the equation the polynomial is equal to a norm form attached to the field extension k over q. And for such varieties, Collier-Thelin has conjectured what a solution to the Hasse problem should look like. He conjectured that the Brouwer-Manin obstruction should be the only obstruction to the Hasse principle and weak approximation for smooth and projective models of the variety defined by the equation we just met. We know this conjecture in a good number of cases, and for the purpose of this discussion, I will restrict attention to the case where the polynomial splits into linear factors over the ground field. It should be mentioned that cases are also known in a setting that goes beyond this one. So in here, the notation is chosen in such a way that the EJ denote the distinct roots of the polynomial. Now here are some known cases. First of all, in work by Swinnerton-Dyer, together with Collier-Thelin and Skol-Bogatov, which is conditional under Schinzel's hypothesis, the conjecture has been confirmed for arbitrary polynomials, so the splitting condition is no longer necessary, and for arbitrary cyclic extensions of number fields. Then Heath, Brown, and Skol-Bogatov analyzed the case in which the polynomial has exactly two distinct roots. It's a polynomial defined over a number field little k, and this result works for arbitrary extensions of number fields. This is a result that is proved by using a combination of the descent theory developed by Polyethylene and Sansup and the Hardy-Littlewood circle method. There was some extra condition that was removed in work by a different team of authors a year later. By using descent theory, but not in combination with the circle method, but instead in combination with results about linear correlations of representation functions by binary quadratic forms, we proved in joint work with Browning and Skorobogatov that the conjecture also holds when you have a polynomial with an arbitrary number of distinct roots and are considering the case of quadratic extensions of Q. So this is a paper about conic bundles. Then, following our work, inspired by the use of results from additive combinatorics in this work, Harpers, Skorobogatov, and Wittenberg went back to the original paper that was conditional under Shinsel's hypothesis and managed to replace Shinsel's hypothesis by a direct application of Green and Tao's results on primes and progressions in the setting where you have an arbitrary number of distinct roots and where you consider cyclic extensions of the rationals. And then we went back and joint work with Browning to the setting of our previous work with Skorobogatov, and we proved that the conjecture also holds in the case of polynomials with an arbitrary number of distinct roots and for arbitrary finite extensions over Q. I will briefly say how additive combinatorics enters into this result. So to prove this result, we apply descent theory, which implies that the conjecture holds provided one can establish the Hasse principle and weak approximation for certain auxiliary varieties. The shape that these auxiliary varieties take is the following. You pick up one equation for each of the distinct factors of the polynomial. So there is one equation for each of these distinct factors here. And on the other side of the system, there appear norm forms. And what is important is that these norm forms occur in separated variables. When you would like to study Hasse principle and weak approximations or study rational points, you can carry out a homogenization and reduce this question to one about integral solutions to a system of equations where you now have on the left-hand side forms and two variables, u and v, and by construction, these linear forms on the left-hand side have the important property that they are pairwise linearly independent. This is essentially coming from the fact that you are looking here at one equation for each of the distinct roots of the polynomial. Proving Hasse principle and weak approximation here is something that you can now do by studying linear correlations as occurred earlier in the talk. In order to study Hasse principle and Hasse principle and weak approximation for such varieties, you have to introduce a counting function that takes into account representations by norm forms. And such a counting function will count for a given integer m how many ways there are to express m as norm form of some element x. And in order to turn this into a finite problem, you might have to quotient out by the action of some subgroup of the group of units. And these are units of norm plus 1. So given such a counting function, the problem of analyzing Hasse principle and weak approximation for varieties given by a system of equations like this, where the Fi now are linear forms that are pairwise non-proportional, is one that can be dealt with by proving asymptotic formulae for linear correlations that involve the representation function just introduced. And this is something you can do using the approach from additive combinatorics. And this is the part that this is the part where most of the work went into our result. I would now like to use the remaining time of this talk to discuss a different result about rational points, which is proved also by analyzing asymptotics for linear correlations. But in this case, it is used by analyzing linear correlations for certain multiplicative functions. So I will start by saying a little bit about multiplicative functions before moving on to rational points again. This is the setup of the linear correlation of linear correlations that I showed you at an earlier point in the slides. And if you go through results in which we know asymptotics for these correlations star, then a lot of cases occur where the arithmetic functions are actually multiplicative. So preserve multiplication at coprime pairs of integers. Such cases include the divisor function, the function that counts representations by sums of the squares if you divide out by 4, and as an intermediate step in Green and Tao's work on primes, the Möbius function has been analyzed. All of these are multiplicative. The representation function that occurred on the previous slide is not multiplicative, definitely not multiplicative if the class number is larger than 1. However, this function can be majorized by a multiplicative function, namely the multiplicative function that counts representations of an integer by the norm of ideals. And this fact that you find a multiplicative majorand has been one important part or tool in the proof of asymptotics for correlations involving such R functions. So the multiplicative structure of functions involved has been important in all of these examples. And I'd been wondering whether one can evaluate these expressions star in general for multiplicative functions, h1 up to hr. This is possible to a very large extent. So it's possible provided the functions belong to a fairly general and large class of functions. It's a class of functions defined by a number of conditions. And in the interest of time, I think I will not say much more about these conditions, but go straight on to give you one interesting example of an element that belongs to this class of functions. So if you take a holomorphic cusp form, for which we know the Sato-Tate conjecture, consider its normalized Hecker eigenvalues, then you get a multiplicative function. And if you take the absolute value of this function, which is still multiplicative, then you obtain an element that belongs to the class of functions. And for such functions, you can, for instance, asymptotically evaluate these expressions. So this has to be enough as motivation for the class being quite general for now. And I want to continue to discuss an application of asymptotics for star in the case where the functions are multiplicative to study rational points. And the question I would like to discuss is one that concerns vibrations over the projective line. We take a smooth and projective variety equipped with a morphism to P1, so that we have a vibration over the projective line, which can be thought of as a family of varieties. And then you might ask how many varieties there are in this family and this vibration that have a rational point. This is a counting question, and in order to turn this into a question you can actually work on, you need to introduce some order in which you count the varieties in this family. And this is done by introducing a height function on the basis, so a height function on the projective line, and then you order the fibers in the vibration by the height of the base point. And then you can introduce a counting function which counts how many points there are on the line up to height b, such that the fiber above the point has a rational point. Since it's sometimes hard to find out whether there exists a rational point or not, the following related counting function is also discussed. We count how many fibers are there up to height b, such that the fiber above the point is everywhere locally soluble. The latter counting function has been studied in work by Logren and Smeets, who prove asymptotic upper bounds in a somewhat more general setting. Their work is a generalization of work by Serre on conic bundles, and both Serre and Logren and Smeets ask in their papers whether the asymptotic upper bounds they obtain are actually sharp. Now, in joint work with Logren, we prove, in the case of vibrations over the projective line, matching asymptotic lower bounds under a couple of conditions. We assume that each fiber in the vibration has an irreducible component of multiplicity 1. We assume that each non-pseudo-split fiber lies above a rational point. This will be defined in a moment. And we assume that there exists a fiber above a rational point that is both smooth and everywhere locally soluble. Non-pseudo-split. The notion of splitness means that there is an irreducible component of multiplicity 1, which is geometrically irreducible. Such a component is fixed by the action of all elements of the absolute Galois group. If you weaken this notion, you arrive at the notion of pseudo-splitness, which means that every element of this Galois group fixes some multiplicity 1 component of the variety viewed over its algebraic closure. That means making an assumption about non-pseudo-split fibers is actually a weaker condition than making an assumption about non-split fibers. This result here is proved using asymptotics for linear correlations of multiplicative functions. And I would like to explain roughly how we arrive at this lower bound. Our strategy is to find a sufficient condition for a point to lie below a fiber that is everywhere locally split, and then produce asymptotic lower bounds for the counting problem that is attached to this sufficient condition. And before I describe how this sufficient condition arises, I would like to motivate why multiplicative functions can be a good device in order to study vibrations over the projective line. If you look at a vibration over the projective line, you might take a point on that projective line, a rational point. So if you write it in primitive coordinates, meaning s and t are integers that are coprime, you can attach to this point a linear form that vanishes at this point. So the linear form, if you choose a primitive, is of the shape as written here. And it has the very nice property that if you take a different point on the projective line, let's assume S and T are primitive coordinates for this point, take a different point on the projective line, consider this linear form evaluated at the point ST, then a prime divides this linear form if and only if the point ST is congruent to the point theta, the point S theta T theta, modulo P. And now if you look at a completely multiplicative function that takes values n 0, 1, and evaluate this multiplicative function at such a linear form, at coprime st, then this expression takes the value 1 if and only if the function takes the value 1 at all primes that divide the form, or if and only if the function rho takes the value 1 at all primes for which the point st is congruent to this original point as theta t theta modulo p. And that means that if you choose your function to suitably to encode algebraic information, then you can access this nice congruence condition and the fact whether or not it holds through a multiplicative function. And this is what is used in a construction for the sufficient condition of a point to lie below a fiber that is everywhere locally soluble. So to construct a detector, we construct certain completely multiplicative functions which at primes take values given by the indicator function of a certain set of primes, which is a set of primes at which the Frobenius element and a suitable extension acts with fixed point on irreducible components of multiplicity 1. So you construct a multiplicative function that encodes some algebraic properties. And with a choice of such function, where you have one such function for each base point of a fiber that is non-pseudo-split, then you arrive at the following property. If you multiply these multiplicative functions evaluated at the respective linear forms, if you multiply them together, this expression takes the value 1 only if the point st lies below a fiber that has a QP point for all sufficiently large primes P. And that almost gives you the sufficient condition that we are looking for. What is missing is information about small primes and about the real point. So at small primes and the real point, you make use of a different assumption from the statement, namely the assumption that there exists a rational point on the projective line, such that the fiber above that point is everywhere locally soluble and smooth. This assumption allows you to use the inverse function theorem to deduce that whenever you look at a point on the projective line that is sufficiently close to this point S0, T0 in the real distance or in the p-adic distances corresponding to small primes, then you can assume, then you can guarantee that this new point ST also lies below a fiber that has a QP point at small primes and that has a real point. So our sufficient condition can now be expressed related to a counting problem, which is to count the points on the projective line of height at most b, counting points on the projective line means that we have to ensure that the coordinates are coprime. We count only points that are sufficiently close to the point S0, T0 in the real distance, which is encoded in this third condition. And we introduce a congruence condition that takes care of the point ST being sufficiently close to S0, T0 and the p-adic distances at all primes that have to be taken care of here. And then we sum over the indicator function that comes from the previous slide. So in this counting function, in this counting problem, we really just sum over points ST that lie below fibers that are everywhere locally soluble. And it's now sufficient to prove asymptotic lower bounds or asymptotics of the correct order for this counting problem. If you look at this, the left-hand side here, you are looking at a sum over a product of multiplicative functions evaluated along a system of linear forms. The system of linear forms turns out to have the correct properties in order to apply results about linear correlations, as mentioned before. The functions that occur are multiplicative functions, and the summation conditions do not quite have the shape they need, but these summation conditions can nonetheless be handled. And we complete our proof by showing that the functions, the multiplicative functions that occur here, actually are functions that belong to this general class of functions that I did not manage to say all that much about. This concludes the description of a second problem that was solved using input from additive combinatorics. And with this, I would like to end my talk.
Many thanks, Lilian, for this very clear and deep talk. Please unmute your microphones and let's thank the speaker. So we have ample time for questions. So, questions, please. Yeah.
So the last theorem, is it, if you specialize to the case of equation y squared minus az squared is equals product of t minus ei, this is exactly a situation like this. So is the last theorem is how much more does it involve in the proof than what you needed for the first theorem?
So in this,
in the case when you had a family of conics over,
yes.
over P1.
So in this result,
yeah, the question is whether it's a complication, the complication because of the Galois action, or is there more from the combinatorics point of view?
From the combinatorics point of view. So if you can compare the combinatorics input that comes in here, you have to evaluate linear correlations for functions that are that are 0, 1 valued. They're just indicator functions. While before you were looking at certain representation functions. If you look at these representation functions, you always have additional arithmetic information encoded in the type of object that you are counting representations for. That makes things a lot easier. So when you try to evaluate these expressions for multiplicative functions in general, you lose a lot of input that was used before. The proofs look very different. There are new technical issues that occur. So it's a completely new result.
Okay.
And in this case, the functions, they have a fairly sparse support. So there are lots of complications that come in when you want to really obtain in this result the correct order asymptotic information for the counting problem.
Okay. Yeah. Thank you.
No problem.
Any other questions, please? Yeah.
Do you get precise estimates for the number of points of bonded height on the vibration?
For the number of bounded height,
Of points of bonded height?
well, we lose some information in this detector approach at primes that go into the exceptional set. So primes that are unramified, you lose some information because you have to take out, you have to, yeah, I don't know. You lose a lot of information at primes, at small primes, everything that goes into S. And I think that is a problem.
Thank you.
Okay, any more questions? Okay, if not, let's thank the speaker once again.